All right, so topic 13 is central limit theorem and confidence intervals, but I'm actually going to use this this study group to also introduce statistical testing, because I feel like statistical testing, understanding statistical testing somewhat ties into confidence intervals as well. So I wanted to start with that actually. So as we'll see here, today we'll talk about statistical testing, because yesterday we actually brought up the z-score, but didn't really talk about what that was really used for. So I wanted to bring us back to that. And then I'll get into the central limit theorem, which is quite important. Multiple interviews, people have been asked, explain what the central limit theorem is and what the implications are. So look out for that. That will be tomorrow's warm-up question in case anyone wants to think about it. We'll talk quickly about sampling, confidence intervals, and then the t-distribution. But the main thing I think for this study group to take away is the structure of statistical testing, which is going to be a very similar structure that we're going to see for the next few study groups, because we're actually going to be talking about different kinds of statistical tests. And so the structure for every statistical test is the same, and this is where I'm going to be introducing that structure. And then also understanding the central limit theorem. Although this section is called confidence intervals, I will say in our data science curriculum, we don't use confidence intervals the same way as traditional statistics does. In our context, we will see confidence intervals as we're doing our linear regression. And so the interpretation for that is actually slightly different. So I'm not going to spend too much time getting into this traditional stats definition, but rather when we get to linear regression, you'll just see the term confidence interval, see that, all right, that is a thing that I know exists in statistics, but the way that we will interpret it will be slightly different from the traditional sense. Definition-wise will be the same, but the way we go about interpreting it will be different. So just to let y'all know, if confidence intervals is something that is really tripping you up in terms of like what it means and what it does, not to worry. I think with linear regression, it becomes actually a little easier to interpret since all the numbers are already there. Any questions before we like start diving in? All right. To start, our first statistical test. Here I have a scenario set up. So let's talk about the scenario first. Here we have a data scientist that wants to examine if there is an effect on IQ scores when using tutors. To analyze this, she conducts IQ tests on a sample of 40 students and wants to compare her students' IQ to the general population's IQ. And so she's doing IQ tests on her sample of students that have been tutored. So the way an IQ score is structured, we know that a standardized IQ test has a mean of 100 and a standard deviation of 16. And when she tests her group of students, however, she gets an average IQ of 103. So based on this finding, can you say that tutoring has an effect? And so this is sort of one of the, I guess, more straightforward examples of statistical testing. You want to see if something has had an effect on a population. And in this scenario, you know what the population parameters are. So overall in the population, just by, I don't know, means of, collecting data here and there, we know that the standard IQ test gives you a mean of 100 and a standard deviation of 16. So knowing that this is a distribution of IQ across the entire population, she wants to see if her group of 40 students is significantly, I guess, smarter than the population. That's what we're testing. So I think if we're not familiar with statistics, we immediately see, all right, 103, yeah, versus 100, definitely smarter, right? However, we're taking into account the distribution of the population, so here especially we have like the standard deviation of 16. So on average, people are about 16 points away from the mean. So also taking into account the overall distribution, is 103 that much smarter than 100? That's just like setting up our problem. And the test of like whether 103 is statistically greater than 100, that will determine whether tutoring does have an effect or not. Any questions about this setup? Okay, great. So for this, we're actually going to use a one sample z-test. This is our first statistical test that we're going to talk about. At the end, after we've gone through all our statistical tests, I will actually send out, actually I can do that today. I'll send out like I'll send up like a summary sheet that has all our different statistical tests and like the differences between them when you would use each one. I think that would be like a helpful summary cheat sheet for knowing what test to use when. I will also preface this by saying not very commonly are we going to be doing statistical tests as data scientists, but they're just good to know. I think it could be a good EDA tool for some projects as well. So again, any questions about this setup? Cool. All right, so this is the statistical testing process. You might see in different resources, they might be like grouped slightly differently, but overall the processes should be the same. So in a statistical testing process, you always have to set up your hypotheses first. And I'm going to talk about how exactly we do that, but we're going to set up a hypothesis for our statistical test. And for every statistical test, you have to set up your hypothesis a little bit differently. Next, based on what your experiment is, decide on what the statistical test is. So for this one, because I had mentioned, is going to be a one sample z-test. We're going to be talking about, I think, 7 or 8 different statistical tests in total. And based on what information you have or what you're looking for, you might want to use a different test. So again, I'll be sending out that summary sheet in a little bit. But for this test of testing this IQ difference, we're going to be using a one sample z-test. Next, you have to pick your alpha. And in, I think, the next couple of slides, I'll explain what that alpha is. We're going to calculate a test statistic. So test statistic is actually, in this case, is what our z-score was. So a test statistic is something that you do have to calculate in every statistical test that you do to determine whether your hypothesis is rejected or not rejected. Next, we're going to talk about p-values, and we'll actually talk about p-values for the next few study groups, and then just interpret what all these values are. And so this is the basic statistical testing process. We're going to see a bunch of different tests over the next few study groups. And in our linear regression, part of the interpretation of the linear regression is also statistical testing. So some statistical testing is going on when we run our linear regression. And you'll sort of see how everything comes together next week. Questions before the next slide? All right. So first off, setting up hypothesis. So every experiment starts with a null and an alternative hypothesis. You might see it denoted as, down here I have H sub 0 and H sub A. So H sub 0 is the null hypothesis, H sub A is alternative hypothesis. You might see H sub 1 as alternative hypothesis sometimes. That's just a different notation, but exactly the same thing. So typically, the null hypothesis represents the situation where there is no effect. And I'll talk about this in context to the question in a little bit. So that would be a null hypothesis. The next thing you have to think of now is whether your test is one-tailed or two-tailed. And so in this kind of statistical testing, we're thinking about whether this group of students is smarter than the rest of the population or has a higher IQ than the rest of the population. If you already know what kind of direction you're looking at in terms of the change in your number, usually that's a one-tailed test because you're only testing for an increase or you're only testing for a decrease. And those are one-tailed tests. Sometimes you have two-tailed tests when you don't know which direction you're testing for. Sometimes you're just testing for a difference. And so if you're testing for a difference, when they don't specify in the question or in the scenario whether it's greater than or lesser than, it is a two-tailed test. And so overall, for tutoring to have an effect, usually we want to reject the null hypothesis because the null hypothesis represents no effect, and we want to reject the null hypothesis that there is an effect. One little terminology thing, you never, so here we're saying we reject the null hypothesis. You never say accept the hypothesis. So opposite of reject is to accept, but you never say that you want to accept the hypothesis. just because the way that, I guess, philosophically statistics works, you can never confirm a belief. You're just sort of like ruling things out. That's kind of how statistics works. So just to like summarize in context now, these are our hypotheses for our question. I wish that bar wouldn't come up. There we go. All right, so our null hypothesis, right at the bottom, we see H sub 0 and represented with a colon of X bar is equal to mu, which is saying the average of your sample, and I should first explain the data before I get into all those like symbols. So the data that we have, the population's mu and standard deviation, mean and standard deviation are 100 and standard deviation 16. So this is our population data. And our sample data has an X bar, and X bar is usually the mean of the sample, is 103. And the other piece of information we have is there are 40 students in her sample. So usually what I like to do, this is a personal thing, but I just like to write out all of the pieces of information that were given just so they're all in one place. And here we'll set up our hypothesis. So our null hypothesis is that X bar is equal to mu. We're saying that statistically, the mean of our group of tutored students is the same as the population. And this is not saying that 103 is equal to 100. This is saying that there's no statistically significant difference between the sample and the population. And of course, our alternate hypothesis is saying that the sample mean is statistically greater than the population mean. So these are just two scenarios. We'll either at the end fail to reject the null hypothesis, which is saying that the null hypothesis still holds true, that there is no effect, tutoring has no effect on IQ, or we'll end up rejecting the null hypothesis and say that tutoring does have an effect, that X bar is significantly, statistically significantly greater than the population IQ of 100. Questions about hypotheses? All right, this is pretty important for like just setting up. But if this is still like a tiny bit fuzzy, we will be going through a lot of different hypotheses over the next couple of days. So no worries about that. All right, so now that we have our hypotheses set up, next thing we want to do is pick our test. And in this case, we already know what test we want to do because it's the first one we're talking about. But in this case, we're going to talk about a one sample Z-test. We'll look at other scenarios in the next few study groups, but the condition for using a Z-test is that you know the population mean and standard deviation. Sometimes you can actually argue that you can never know what the true population mean and standard deviation are. But in this case, because of how the question was asked and the way that the scenario was set up, we can assume that we do know this population mean and standard deviation. There are just going to be a lot of other situations of which the tests we'll see over the next few days where you don't know population mean and standard deviation. So therefore, we're going to use a one sample Z-test since we do know that the population mean and standard deviation are 116. All right, so next, after picking your test, we have to pick alpha. And alpha represents your cutoff value. Another way of saying alpha is also confidence level. And your confidence level is 1 minus alpha. So normally or typically, your alpha is set at 0.05. That's just the most common alpha that's used. We'll see other situations, and also we'll like talk about this once we've done the rest of our statistical test. But you might increase or decrease your alpha based on how much how much leeway you want to give, or how strict you want your test to be. And we'll go more into that a little bit later. So alpha is your cutoff value. And then the way you would interpret your results, you would interpret them by saying with a confidence level of 95%, or you can also say with an alpha set at 0.05, we can reject or fail to reject the null hypothesis that blah, 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 tutoring had an effect or didn't have an effect. So that's how that ties into the statistical test. One thing to mention, you should always set alpha before you conduct your test, just because we'll see later that we're actually going to be comparing certain values to our alpha. And if you already know what that value is going to be, and you set your alpha after that, it's kind of like biasing your test, or you're setting your alpha knowing what your results are. And so that can just lead to a bunch of like ethical things, and you basically don't want to know your results before you set up your experiment. It's just something to remember. Questions about this? All right. Okay, so the next step is we actually have to calculate our test statistic and p-value. So for calculating test statistic, every test has a different test statistic. So for this case, in a one sample z-test, the z-score is going to be our test statistic. And then the p-value is also determined in different ways based on the test. So we'll talk about this example now, but then for future tests, we'll talk about the different ways you can do that. So usually for test statistics, you have a formula that is just known out there that you're just going to plug in your numbers to calculate your test statistic. Good news is in Python, everything's already built in. There's usually a function, probably in like SciPy, that has the method for calculating your test statistic. Usually you just need to give it like your mean values, your standard deviation, basically all of this information, and they would be able to calculate it for you. The z-score formula is not super complicated, so it's pretty easy to like write out over here, but you'll see in future, if anyone has looked ahead at the slides, some of the formulas get pretty intense and we want to just use the built-in formulas. But here, for the z-score, given that we have all of these parameters for our data and our population and sample, we plug in all our numbers into this formula. And I talked about this yesterday. Let me actually just like circle it so it's a little bit clearer. So this is our z-score formula. If you remember, this particular part being divided by the square root of n is when you're comparing a sample. So one difference would be that if you were just comparing to see, is this one student statistically smarter than the population of students, you wouldn't divide it by root of n. But anyways, here, all we have to do is plug in our numbers. We have our x bar, we have our mu here and here. We have these as well. We have our standard deviation and we have our n. And then after we compute that, we end up with a z-score, or a test statistic, of 1.19. Questions about the test statistic? All right, so now that we have our test statistic, again, this is more specific to the one sample z-test or any z-test. For the z-test, you can actually look up the associated probability from the z-table. So let's take a look at the z-table, which I have linked here. And with our test statistic of 1.19, let's look up, let me clear this. Let's look up the associated probability. So if we scroll down, we're looking for 1.19. We have a probability of 0.883. So that's the associated probability with the test statistic. So that means that the average IQ of tutor students is greater than 88% of the population. That's one way to interpret it. For a right tilt test, and I think I have a diagram. I have a diagram afterwards, so I'll like explain that in more detail a little bit. Our p-value is actually going to be 1 minus the associated probability, which in this case is 0.12, which is greater than our alpha of 0.05. I think the next slide is going to tie things all together. But any questions or clarifications on this part? Happy to jump back and forth as well as we think of questions. But I think things will be a little clearer with this slide. I personally actually really like to represent my statistical testing in diagrams because I just think it's easier for me to understand what's going on. So what we have here, this entire bell curve, we're going to use this bell curve as the population of IQ, the IQ of the population, sorry. This entire bell curve is the population of the IQ of the population, and this is standardized. So that's why we can still see that it's centered right at 0. Centered right at 0 because this entire thing has been standardized. So when we have an alpha, so this I actually looked up, your alpha value here, what we're trying to do is see if, you know, your group of students is significantly smarter. So we want to see that our group of students is as right as possible on this diagram. That makes sense. So here, this alpha here, and alpha being set at 0.05 means that to the right of alpha, this area under this curve is 0.05. So that's what this means. I set my alpha at 0.05, and each alpha also sort of has like an associated like place on the graph. But wherever alpha is, with my alpha set at 0.05 means that this area to the right of it is 0.05. So also you could say 5% of the area of the entire bell curve. Does that need some clarification? Basically, wherever my alpha is set, this entire area under any PDF, because this is a PDF, the area under any PDF is, it totals to 1. But where my alpha is set, the area to the right here is going to be 0.05. And why I'm looking to the right is because we want to see some threshold of seeing what the threshold is for that group of students to be considered statistically smarter than the rest of the population or not. That's why this alpha is to the right. So here we have our alpha. Another thing to talk about is that test statistic that we came up with. So that test statistic here is 1.19. And 1.19 is denoted by like the division between the red and the blue section. 1.19 here means that under this entire red area, based on what we looked up in the Z table, this red area is 0.883, right? Because if we looked up from the Z table, and the way that the definition of probabilities that you look up from the Z table is the probability or area under the curve of everything to the left of your Z score. So that means this red area is 0.883. And let me just draw that real quick. So this area, 0.883. And because this red area is 0.883, this blue area is 0.117. Is that right? Yeah, 0.117. The blue area is 0.117. What we're looking to compare values of is we're comparing this 0.117 area to the area to the right of alpha. So this area to the right of alpha is, let me just use a different color. This area to the right of alpha is 0.05. So this is how the diagram comes together. The red and the blue together make 1 because that is where a test statistic is, and 883 is the associated probability, and therefore this blue area is basically 12%. Basically, the cutoff here is alpha. This line is the cutoff. So if the division between red and blue is to the right of alpha, we reject our null hypothesis. And if this division here is to the right, to the left of alpha, we fail to reject our null hypothesis. What we're saying is this line here represents, this division between red and blue represents our sample of 40 students. The alpha represents our cutoff. Because we want to see if they're significantly higher IQ than the population, we want this cutoff, we want this 1.19 to be greater. We want ideally for this to be as close to the right side as possible. However, in this case, it doesn't pass our alpha threshold. Therefore, by conclusion, we say that actually no, they are not significantly at a higher IQ than the rest of the population. Does that make sense?
So, where would would the 100 IQ, which is the mean for the whole population, be like at 0 there?
Mm-hmm. Yeah, that's right.
deviations. So the difference between a 100 and a 103 is like 33% more. Like, because the 100 would represent that you're smarter than 50% of the population, right? Or no?
Actually, yeah, because that would be your median. Yeah, that being your mean value. Yeah, if you hadn't, yeah, I would agree with that. That if you were smarter than 50% of your population, then yeah.
Like if you had an IQ of 100, you'd be smarter than 50% of the population. Whereas if you have an IQ of 103, you're supposed to be smarter than 88% of the population. But in order for it to be statistically significant, you need to be smarter than 95% of the population.
Yeah, exactly.
Okay.
Yes, that's a really good way of putting it. But yeah, any other like clarifying question? I know there's a lot going on here, but basically I like to think of this alpha as like a threshold, and only if you pass that threshold, there is statistical significance, and if you don't pass that threshold, you don't. And this division between red and blue is what we're testing.
Question.
Mm-hmm.
But if our population standard deviation is 16, then actually you have to be 116 to be greater than 67% of the population. So the numbers aren't really translating. It's because of the sample size, I guess.
Yeah, that's right. If you were testing for a single, if you were testing a single person, then yes. Just because if we go back here and excuse all of this first, yeah, it's because we're taking a look at a slightly smaller standard deviation. That's just the way that samples are calculated. But yeah. It does make sense that, yeah, because if you had, let's say, one person, and if you have one person and you were, let's say this was not being divided by this value, your z-score would end up being 3 out of 16, right? And so to have like a one standard deviation, you would have to have an IQ of 116 to be one standard deviation across the mean. But because we're comparing like a group of people, we reduce that standard deviation. That's right.
Also, it would be more than 67 because that's just within the standard deviations. You also have the ones which are lower than the standard deviation on the left.
Let's see. That is I'm not sure if I'm understanding it.
I see what he's saying.
67% within one standard deviation of the center.
That's right.
So
yeah.
then you also have those to the left of there.
Yeah. The tail on the other side.
Yeah, that's right. Because 67% would be like only, let me use a different color. 67% would only be between this and this. But yeah, I think the main thing that we're getting at here is we want to compare our alpha value to the probability that we get from our z-score. All right. I will say z-tests are probably like the simplest tests, unfortunately, but not used very often because we don't often know the population mean and standard deviation. Right, that is just like the structure of a statistical test. I will say that also what's going to be more important for us is that we're going to see a bunch of models that do this statistical testing for us and output things like p-values, we'll see t statistics, but in this example, we looked at z statistics, and we'll just need to be able to interpret what those are. We won't actually need to like set up tests and conduct these tests as data scientists. But, you know, just good to know of this process. Let's see what's after this so we can see what to move on to. Yeah, all right. Before we wrap up with statistical testing, anyone have any clarifying questions? I think we will be seeing multiple statistical testing examples over different kinds of tests. So hopefully like this whole like alpha comparing to p-value thing will get easier to understand. All right. Let's move on to the central limit theorem. So central limit theorem for us, it actually has a very important implication, but what's really important to note is what it is. That is, like, unfortunately kind of a common interview question. So I would say just find a definition of central limit theorem that makes sense to you, and then honestly remember it. So the central limit theorem states that independent random variables summed together will converge to a normal distribution as the number of variables increases. The definition that I actually like to use is the second one, because to me it's a little easier to visualize. The other definition is that the distribution of sample means of any population as the sample size increases will converge to a normal distribution. What that means is, if I have like some population and I don't know what kind of distribution this population has, if I were to draw a bunch of samples from this population, just over and over again, draw a bunch of samples, and with each of these samples, I record the mean of the sample. So if I'm recording a bunch of the means of the sample, and I were to plot it in a distribution, it will converge to a normal distribution with more samples, as I take the means of more and more samples. Does that make sense? I think there's one lab that actually has you simulating that, like drawing a lot of samples from a population and actually taking a look at how it does converge to a normal distribution. So that's something that's pretty cool to look for.
Is it just for the mean? Or
Mhm.
could you take other, I don't know, like variables or parameters out of a
Yeah. If anyone knows, correct me. Yeah.
Converge to a
Yeah.
normal distribution?
If anyone knows, correct me if I'm wrong, but I do think it is the same for a standard deviation, but I have to look it up. But I can definitely confirm it is for the mean. I think it's true for standard deviations, but I don't remember off the top of my head.
Like, what does it mean when they say independent random variables summed together, I guess?
Yeah. I guess you can think of it as, imagine, let me think of an example. So let's say you have it's kind of, I will find resources and then send them out. I think that'll be easier. They'll do a way better job than I can at explaining what that means. But there are a couple Medium articles I know that explain this pretty well. So I'll send them out. I will send them out to the Slack channel in a little bit.
Thank you.
You're welcome. Yeah, the reason I use the second definition is because I personally don't fully understand what the first definition, it doesn't really click in my head either.
For independent random variables, couldn't it be like explained as if you have a population and then you randomly select a sample from that population, then each of those people in there are technically independent random variables? Like
Yes.
one individual?
Yeah. That's right. Yeah. That is correct. The other part that is important for interviews, and a common thing that people will ask is, what is the implication of the central limit theorem for data scientists? And the main reason why the central limit theorem is so important to us is the central limit theorem allows us to use sample statistics to make inferences or estimates on the population. We'll talk about parameter estimation in, I think, section 17, but basically based on the central limit theorem, let's say again, we don't know anything about our population, but because we know that taking a bunch of samples and taking their sample means, as it converges to a normal distribution, we can sort of make an inference that, this population mean has the same mean as this normal distribution of sample means. I think
You would basically
Mhm.
look to see that the mean wasn't like very many standard deviations away from the mean of all the sample means. And then you would like, so if it's kind of in range or similar to what you estimate the population mean to be, then you would say that the sample's like kind of representative of the population. Is that
yeah, kind of. Yeah, I guess to like rephrase that, if you imagine like you have no idea what the population mean is, and you want to sort of be able to estimate that, one way of going about estimating that would be to keep taking samples from your population. So let's say you want to find like the average height of everybody in the world. You just survey like 20 people at a time, and each time you just record the mean height of that sample. And basically you're going to end up with a distribution that is fairly normal. So you're going to have like, you know, a bunch of values. I don't know what the average height of people in the world are, maybe like 5'9", 5'10". So you're going to maybe get like a bunch of heights around like 5'9", 5'10", and then fewer heights on the higher end and on the lower end. And these are going to be data points that you collect that are the means of your sample. Basically, with this data that you've collected, you can make a pretty fair inference that your population mean is going to be the same as this mean of your sample means. Does that help? Does that help a little bit? Yeah, again, this gets into like pretty like theory heavy stats. So I will send out like a couple articles that I think are helpful for understanding this.
I had a question as well.
Mm-hmm.
So on the second definition, it says as the sample size increases, it will converge to a normal distribution. So is it the sample size or like the number of samples that you're taking?
That's a good one. It's number of samples. Is the number of samples increases.
Okay.
Yeah, I will clarify that. Yeah, number of samples. I don't think I can change the PDF on your repo, but I'll make a note that it is number of samples increases. Thanks for that.
I'd like to share like the way I think about it.
Yeah.
Is like if you're trying to find the average height of 1,000 people and you pick 10 people at random and you find the average height, that won't tell you very much. But if you take 10 different samples of 10 people, it'll look a little bit more like it. Then you take 100 samples of 10 people, it'll start over and over to look like the curve, the normal distribution of the heights. So that's how I think of it. I need a practical example to understand these things.
Yeah, I think what might help for this one in terms of like visualizing, there is a lesson, and I'll actually look for the specific one and I'll Slack it out to you guys. But there's an actual example where they give you this like really weird looking population and you're just going to be taking samples from it. And the more samples you take from it, they'll actually in the lab have you plot what that looks like. And the more number of samples you have, it does start to look more like a normal distribution. So I'm going to look for which lab that exactly is and just let y'all know where that is. All right, but important to like find a definition that you like, because they do ask this at interviews. Questions before we move on? I think right after this, there's a little bit more. Cool. All right, so sampling statistics. This we're talking about this because we're going to talk about confidence intervals right after this, and confidence intervals we'll be talking about in the context of a T distribution, which is actually going to be the distribution of our next few statistical tests that we're going to talk about tomorrow. So just so you know, standard error here is very, very similar to standard deviation. And basically, same definition. The higher your number, the more spread out your data is. I'm going to also send out like a really good StatQuest video that explains standard error much better than I can. So I really highly recommend taking a look at that one. But basically, standard error is for sample data and standard deviation is for population data. So the reason why we were earlier in our Z-test dividing our standard deviation by the square root of n is because it was sample data rather than a single point. And the calculation for standard error is if you have, the calculation for standard error is you can approximate your standard error by calculating the standard deviation of your sample. Let me rephrase that. I said a bunch of like random words. You can calculate your standard error of your sample by using an approximation of your standard deviation. So basically, if you need to find standard error, you would just take sigma divided by root n, same formula. So yeah, sigma here is the population standard deviation, which we're approximating with the sample standard deviation. I don't think I explained that very clearly, but I will send out a resource for this. What questions about this? All right. Okay, so this is the last thing we're going to be talking about, confidence intervals. And where we will see confidence intervals as data scientists, we will literally just see test statistic, and they'll actually just give you a confidence interval. That is very different from these confidence intervals, because these confidence intervals are ones that are constructed. So in some of the labs, you'll be asked to construct confidence intervals. And basically, those are ranges of values above and below a point estimate. And a point estimate is just like a parameter like mean or standard deviation. And it does capture the true population parameter at some predetermined confidence level. So a definition for that is you decide on how wide or narrow you want your confidence interval to be. Usually 95% because of alpha as 0.5. I think it's because of that. A 95% confidence interval means that 95% of the confidence intervals that you're constructing will contain the true population parameter. So confidence intervals are used when you're estimating things. And basically, when you're estimating something, you also can give it confidence intervals. And when you have a 95% confidence interval, it means that 95% of the confidence intervals that you will construct in the same manner will contain the true population mean. In reality, we are not going to be calculating a lot of confidence intervals. That's just the way we correctly define a confidence interval. Because, contrast to that, a 95 confidence interval does not contain 95% of the values. That's just like a common misdefinition. So all you do with calculating a confidence interval is you take the mean plus and minus your margin of error. And what your margin of error is depends on your underlying distribution. So here, if we know this population standard of error, your margin of error will be given by this formula. Your z-score multiplied by your standard deviation divided by root of n. And again, the z is the same z-score that we're using for our z-test, and also can be looked up on the z-table. So, questions about that first before we move on. I will say this particular way of doing confidence intervals is not the way that we will be using confidence intervals. We will literally just be given numbers, and we just need to be able to know how to interpret them. And the way we interpret them will be that, okay, given that we have this confidence interval, and they will usually give you like a smaller number and a bigger number, the way we interpret them is that, all right, 95% of the confidence intervals that will be constructed like this will contain the true population mean, or the true population parameter. And then it also depends on what the confidence interval is constructed for. Questions? All right. I will say very, very common for like students between like topics 12 through 15, 16 to be like, I have no idea what's going on. But when we see things in context in a linear regression, it'll make a lot more sense. I think just being, I think just being thrown these definitions and like letters and like phrases of statistics, and seeing that come together when we do a linear regression, it'll make a lot more sense. I promise, I swear. All right. So here, confidence intervals, we have to talk about the t-distribution. Now, earlier we actually dealt with a z-distribution. Z-distribution is synonymous with the standard normal distribution. So earlier when we were dealing with this statistical test, you can see here that this distribution that we were using here was the standard normal distribution, or z-distribution. The other kind of most popular distribution we're using is the t-distribution. So if we remember with this distribution, what are some of the factors that, what are the conditions that have to be met before we can use this? We need to know our population mean and standard deviation. So if we don't have that information, and let me just go over here. For a t-distribution, we would use that when we don't know our population standard deviation. And so whenever we're using a t-distribution, it's when we don't know the population standard deviation. And tomorrow's statistical tests that we will look at are going to be scenarios where we'll be using the t-distribution and t-tests. And I will say t-tests are probably the most common kind of statistical test. When we talk about A/B testing, we will be conducting t-tests. So t-distributions are used when we don't know population standard deviation. With t-distributions, we actually have a new parameter that we have to consider, which is the degrees of freedom. Basically, the more degrees of freedom you have, the more like a normal distribution your t-distribution will look like. So basically a t-distribution, I don't know if I can zoom in on this. Not really. All right, so if we see this first graph over here, the blue line is a normal distribution, and this red line is a t-distribution. It's a t-distribution with just 1 degree of freedom. By default, a t-distribution is looks very similar to a normal distribution, just has heavier tails. So the tails are a little higher, and because of that, if we want to maintain a area of 1, because of that, the peak is not as high as well. And when you increase the degrees of freedom in a t-distribution, it starts to look more and more like a normal distribution. That's just a fact to remember for what's coming up. So typically, our degrees of freedom are calculated by the number of items in your sample minus 1. And again, the video that I mentioned I'm going to send out will talk about this as well. But the degrees of freedom are determined by n minus 1. It sort of brings back things about the central limit theorem as well, because t-distributions are when we don't know this population standard deviation. And let's say our sample is very, very small, it's better to use a t-distribution. However, if we have a sample size that is much bigger and takes up a bigger proportion of the entire population, we can sort of be more okay with assuming that it's more similar to the population. So therefore, we don't have to estimate it with a different distribution from the population. Cool, all right. This t-distribution stuff will make a little bit more sense, I think, tomorrow when we talk about t-tests. But just as some definitions, to calculate a confidence interval with a t-distribution, these are the formulas. Also in good news, SciPy has it built in. You can just give it all of these numbers of these symbols and it'll calculate it for you. But this is the exact same formula that I had a few slides back over here. Mean plus minus margin of error. So this is the formula for z-test, but for t-test, it's like this. Your mean plus and minus margin of error. And over here, you have, here's your point estimate of mu, which is your mean or whatever you're trying to construct this confidence interval for. And then these will be your margin of error. So this part over here is your margin of error. Actually, let me like draw it with some boxes. This is your margin of error, which is this part, which is this part. That is your margin of error. Your margin of error is actually taken by your t-statistic, and I will actually only talk about t-statistic tomorrow. But you can see here we also have embedded our standard error. So those all make up the formula for constructing a confidence interval. Confidence intervals for us, again, what's more important about it is just interpreting it. So I wouldn't worry too much about like calculating these things. But I think this is the last slide that I have here. Okay, any questions or I guess any thoughts about all of this stuff? Stats is not easy. I will admit that I've taken like multiple stats classes, and so some of it I'm a little bit fuzzy on, admittedly. But again, I will send out resources that will do a much better job of explaining than I can. And also for anything that is super important for data scientists to remember, I will point out. So just to reiterate what's important in this slideshow, first of all, the statistical testing process, just knowing like what things you have to remember when we're conducting a statistical test. Also, the central limit theorem, just remember a definition of that and what implications that has for data scientists. And a little less important, no, actually not less important, but also remember a definition for confidence interval as well. All right, any final questions before I jump off of this? Awesome. Let me stop this recording.